Hello and welcome back to Old School Coding, where we are working on some classic software engineering tasks using some classic software engineering tools and a classic software engineering language to build a classic tool, specifically in C99 and using just a plain old editor called Emacs. Plain, yeah, I keep calling it that. It's not. So using Emacs and GCC and the C99 programming language, we are producing a discrete event simulation, eventually simulating a 1980s era microcomputer of some sort. I have in mind something 8080 based, possibly an MSI or an Altair, possibly a Sol 20. Or if we decide to go a little more modern, I have enough information that I think I can produce something that works kind of like a Stratos Z80, which was a Z80 machine of the day that sported 80 kilobytes of memory. And yeah, 64 kilobytes of address space, 80 kilobytes of memory. They shoved 16 gallons of water in a 10-gallon hat. It was clever how they did it. Anyway, little known computer that I happen to have loved at the time. So the plan for today is to work on the scheduling mechanism. So we have our idea of a step, which is a function with a parameter that you pass it. We have an idea of a list of steps called a subscribers list, where for some reason you want to notify a bunch of people that something happens, so people can add themselves to the list, and when you run the list, it calls all of the events. We have the notion of a step at, which is a step that runs at a specific simulated time. And no queuing there yet. That's what we're working on today. But when you run the step at, it sets the simulated time to its designated time, and then it runs its task. And all of these have some power on self-tests. They all have invariant checkers. They all have built-in self-tests that run a little bit longer, quote unquote. Currently, they're all trivial. And then there's a benchmarking scheme. The idea is that you would run the power on self-test anytime the program starts. You would run the built-in self-test on demand, but make that part of your build. So your build loop is build anything that's out of date and rerun the program to trigger the power on self-test, and then rerun the program to do the built-in self-tests. Do that in one run. And then do the benchmarking. Currently, our main program doesn't take any parameters, just runs post and bist and bench, but all in a row. So that's where we are. Before I step into doing the scheduler, I want to do a little bit of refactoring because I was thinking last night, and I think one of our routines, it's this one right here, subs add, does a little bit more than I like. Now, you may notice that my margins are a little more narrow today. I popped up my stream this morning, and YouTube did not want to stream at my native resolution of the monitor. I realized, yes, indeedy, I was streaming ultra wide. So I've stepped back to 2560 by 1440, aka 1440p. And that means that my code sometimes will be a little bit longer than it should be. Now let's maybe run the formatter. So I need to adjust my formatter to make my code a little more narrow. So we get into our indent profile here. .indent.pro. And this is old school, the way you did these things. Now, I was set up for, say, 132 columns, which is my line printer length thing. I'm going to run that back. I'm going to run 96 columns. Actually, I was doing 124, leave myself a little margin. Let's bring that back to 96. Now, 96 columns, do I actually have 96 columns wide in the editor? No, I don't. Okay, so, yeah, okay, we're bringing it back to 80 columns. We're back on Hollow Earth cards, guys. Now, we're actually 80 columns plus some margin, so I can just set this to 80 rather than 72. That's the, there is L80. Okay, so now when I indent the code, it will enforce a right margin at 80 columns. That also means that we have reformatted everything to be that length. Let's take a look at what the damage is. So our command is git status and git diff into cat. So we modified those .c files. We bring it out into this window here. So you notice that all of these lines got wrapped. I'm going to check this into my Git repository now so that we won't see these diffs later on. In fact, I could just do it from here. Shell status git add dot. Let's make sure we are actually working properly. Okay, so after indenting, we have done the rebuild, and there's the evidence. So git status. Okay, so git commit dash m narrow rerun indent with for 80 column limit. There. Bring this stuff back up here. So we're going to go back in and do what we were doing before. So we are here in subs add, which is, it's doing too many things. I like to do just one thing in a function, really. I'm not a fanatic about it, but where it's really doing two distinct things, each of which is a few lines, I like to break it up if I can. So we're going to say we need a function that will make space in the subs for a new thing and return the index of that thing. So static int subs extend. Let's put the declaration at the top. Again, this is following my ancient habits. We're going to put the actual implementation at the bottom of this top section. I'm keeping the test, post bist and bench stuff down below at the bottom so we can carve those off later. When these files get big, we'll actually break the testing code out separately, and any significant methods would go out. So subs extend is going to return the index to write to. So instead of len, this is going to look something like this. Int slot equals to sub extend. Okay. And that will already have increased that. So subs invar s subs extend. Then we're going to gather that stuff. This logic all goes down into subs extend. There's probably a lot of this I'm going to delete, variables that aren't needed and so on. That. So the slot is going to be here. So if len is equal to the cat and so on down there, up top, our logic here becomes extend it, giving us a slot number, then write to list and subs in var. So all we need is slot and list. And because I am paranoid, I'm going to come down to subs extend, and I'm going to check the invariants at the top and the bottom. Now, there is going to be a issue here. When we do this invariant check, we have extended the length of the guy. Okay, so here we need to say s arrow len equals slot plus 1. Actually, I don't need to have something called slot. So we're returning the old len. There's two ways I could do this. I could either modify the invariant to say the length may include a trailing element, or I can delay this for after. I'm going to delay it for after. And now I need to say subs s like that. So is this what we want? Subs add says invariant, determine the slot after we extend it, grab the list and write the stuff and check the invariants. Oh, we no longer need these. That little void thingy is a way that I can flag that, yes, I know this is not being used. Don't warn me about it. I need to make sure I get rid of them once I've implemented a function. So subs add now becomes simple. Subs extend gets the extended logic for doing this. Make sure we're doing the right thing. Cap, len, and list. If length is equal to capacity, then extend the capacity, reallocate, error check. List equals copy. Well, we don't need list after this, so we can just say list there equals copy. Cap equals new cap. And then down at the bottom, we can bump len because len is less than cap. I'm going to check the invariant before I increase len. So the state of S of subs when I return will be it's meeting its invariance for all except after I bump len by 1. So we are not quite fixing the invariance. But in order to make it so the invariant passes when subs extend returns, I would need to include some additional state here, which would say we have an empty entry at the end. Well, we're actually going to need this for the heap, because when we're doing a heap, we might be checking invariance with an empty entry in the middle. So I'm going to put in something here called bubble. So I'm defining bubble as bubble is an entry in the list whose contents are undefined. And therefore, we can check everything else, but we can't check anything to do with the bubble. So what is the consequence of having a bubble? Well, the consequence of the bubble is I can't check the invariance of the bubble. Okay. This is too nested. So if capacity is equal to 0, I want to return. If the length return. There. So there are two schools of thought on single return. The concept itself grew out of the 60s, where you might have had bad Fortran, where a given bit of code might have multiple entry points and multiple exit points. And this could get very confusing. And people realized that if you had a single exit point, then you could put the stuff at the exit and everybody leaving the function would go through it. And this is really cool. And these days, in C++, for instance, you have RAII, where when you leave a scope, you can deconstruct any objects you built at the top of the scope, and that's great. So that handles that. And that's handled no matter how you leave it. So for C++, you don't have quite the motivation to have a single return in a scope, because you still go through the RAII shut things down stuff. But back in C, there is this idea of having a single point of return. But what it comes down to is we would have either, these would be, if cap equals 0, go to the bottom, and at the bottom we would maybe do something in return, or we'd have that big nested structure. It gets deeper and deeper and deeper. So if I've got 17 guard clauses for when I do or do not want to do some code, that would be nesting 17 levels deep. Ooh, or it'd be 17 go-tos. Eesh. I would rather keep the function simple and have guard clauses early in the code that says, if this condition is true, our job here is done. Boom. And have it set up so that I don't have to have stuff down at the bottom that everybody runs, because I'm not complicated enough to have anything that has to happen as my function returns. So there we go. So we've introduced this thing called bubble. What do I want to assert about bubble? Let's assert, so bubble can be 0 up to but not including len, or it can be -1 saying we don't have a bubble. So s arrow, so we can say s arrow bubble is greater than or equal to -1. I'm not going to let it be -2 or -3. And I'm going to assert that it is less than s arrow len. I think just for sanity, I may want to set the bubble to the length. So I may have the bubble following length at some point. Let's make that well defined. I don't know what I'll use it for. I have an idea what I might use it for, but I don't want to say. But let's allow bubble to be before the first element or after the last element. And that may simplify some logic. If we never use it, I can tighten up this invariant. But for now, I'll just put that in the invariants. I want to, well, hold on. This would then be asserting that len, something about len before. So we were saying before that if the capacity was 0, we didn't check anything else. I think I'm going to want to put in a few more checks before I do an early return. So I'm going to assert that the capacity is greater than or equal to len, and I'm going to assert that len is greater than or equal to 0. I could just simply make these unsigned, but no, I didn't, so I won't. And so we're going to assert ordering between len and capacity and bubble like that. If capacity is 0, we're allowed to have a null pointer for list. If len is 0, we don't need to do anything down here, but this is redundant because the loop would simply not execute, so we could do that. Or I can do this. If capacity, then assert list. And then we go through there. And I will have more things I want to check here. The reason why I'm doing this is that this subs is going to be the foundation for the code that implements the heap. And it's going to basically clone to own on the structure of the list. So we're going to, for our heap, we'll still need to be able to extend it. It'll have additional invariants that it wants to apply. So if I is the bubble, then we don't want to assert anything at all about the entry. We've still tested all of this stuff. So now down here, we can subs extend. So what do we want to do anywhere else if there's a bubble? Subs init needs to set s arrow bubble to -1. Subs add will extend and use the slot. I think what I'm going to do is inside subs extend, because I'm going to be setting bubble, I want to assert that bubble is -1. Must not have a bubble when present during subs extend. So I'm not going to allow a bubble on entry to subs extend. The alternative is that if I've got a bubble, I want to use it. Oh, that's better. So if s arrow bubble is greater or equal to 0, so if it's an entry that I can use, I'm going to use it. And s arrow bubble less than or equal to s arrow len, oops, less than len. Like that. And easiest is if we go ahead and start initializing these. So I'm going to need len like that. So if bubble is something we can use, then I'm going to say s arrow bubble equals -1 and return s arrow bubble. There. And if bubble was beyond len, then it's what we're going to use already. I'm not going to worry about it. So if it's something we can use, we use it. If it's not, we're going to ignore it. So subs extend then conceptually will discard bubbles that are outside the active area. So if len equals cap, then we reallocate. I don't like the way that indents just like that, so I'm going to do void star copy here, like that. And len equals cap, we're extending it. Now again, subs extend is getting extended, so it could be that what I should do is do this bubble in its caller. That actually makes more sense. So instead of doing, so extend will say we're extending it, we don't have a bubble. We're going to do it add, we're going to say, there. So slot will be where we put it. So if we have a bubble, then we're going to say slot equals bubble. Oh, wait a minute. So there's our, if we have a bubble, we can use it. Otherwise, we have to extend it. Okay, so I like that logic better. That says if we're adding, we can use the slot or extend. And if we're extending, we say assert s arrow bubble is equal to -1. Len cap and list. So now all extend does is check invariance, make the array bigger. We are going to say s arrow bubble equals len. So we're going to exempt the new entry from the invariant check. We're going to check invariance and return the new slot. Let's call it slot because it's not going to be the length. There. So the slot we want to use is slen. Slot equals cap, we extend. If slot, assert slot is less than cap, bubble equals slot. Len is that, in var, return slot. So it's a good thing that I moved extend out because this actually would have been, it would have increased the complexity rating of subs add beyond what I want. Now, complexity is a measure of how much effort it takes to comprehend and to completely test a method. McCabe proposed this standard, and it's been modified. I use the modified McCabe, where basically you count the number of branches. So subs add, we've got, you start out with 1 for a sequential list of things. This if, this makes it 2, this makes it 3. So this has a complexity of either 2 or 3, depending on how you count if else. And you would need to make 2 passes through this function to cover all the paths. So in reality, I think that means it's a 2. If we had 3 ifs in a row, that would be 3 complexity points. I have noticed that when you count like that, if that count gets up to around 10, you're looking at a function that probably is doing too many things. And the way you get around that, if you have one function that does one of n things, you make a switch. And switch, in the modified McCabe, the whole switch counts as 1. Because conceptually, you're doing an n-way dispatch with one thing. Realistically, I find that if I've got a switch of 16 statements, its complexity is more like 1 than 16, but it's above 1. So I don't know how to handle that as a mathematical thing, but if you use the complexity as a kind of a notion, and then you say, well, this construct I'm not as comfortable with as a 1, or you say, well, this is 500 lines of straight line code with no conditions. Is this really a 1? This is not. So you have to use your judgment. You can't take all engineering judgment and run it down to just a list. Okay, so it's important that we don't snapshot list until after subs extend is returned. So there, and len and slot, len will have changed. I don't use len in this function. So we're going to fetch slot from bubble, and then we're going to reset slot here if it turns out that we've got a bad slot. So try this slot, and if it's not valid, try that slot. So let's take a look. I've done a whole bunch of editing, and we have an error. We have a static int subs extend parameter names without types in function declaration because I forgot to say subs. And I don't need the name of the parameter because it's obvious what's going on from the type. And this now says test condition failed. And the test condition that failed is that the start val didn't ever get incremented. So I just did a whole bunch of refactoring, and I messed up the code somewhere, and I didn't do a good job of checkpointing and refactoring as I went. So I need to put in some debugs. So subs init set bubble to -1. We set bubble here. Oh, right. Okay, I'm messing with bubble. When I extended it, I set the bubble to the new entry, didn't I? But once I have written this, slot is now valid. I need to set bubble to -1. A bubble needed to be set here where I'm going to do a subs in var of s. So this is the invariant check as we come out of subs extend. During development, I really like having a lot of redundant invariant checks. And I will remove these from performance critical sections of the code as time goes by. So clearing out bubble, there we go. And I really should say if slot is equal to s bubble. Just belt and suspenders. So again, some of this code is overkill and can be removed later when we start optimizing the code. And I am going to be spending my time thinking about optimization only on critical code sections. And I assert that subscription lists are things you set up during initialization, and they don't change at runtime. So at runtime, people generally do not add to the subscription list. Notice that there is no method over here for removing somebody from subscription list. Okay? So these are intended to be static. If we need to have a dynamic call to a list where people can subscribe and they can unsubscribe, we will have a separate structure because the critical code path, let's start documenting where the critical code path is. Subs run, this is critical timing path. Because subs run is what we run when we say an edge transition, let's call everybody interested in it. And that is going to be a lot of bits of code. The next one is step run. This is also critical timing path here. Okay. Those are our only critical timing path bits of code that we've written so far. Notice it's We have a pointer to a step. We want to get the function pointer and the argument pointer and make the call. Now for step at, the scheduler is a priority queue. It's a heap, which means insertion and deletion aren't constant time. They take order log n, for n being the number of entries in the queue. So I expect the heap to take longer to run. Therefore, our core executable is not going to be driven by having scheduled things for here's the next clock edge. We're not going to say this clock edge rose, so in 5 nanoseconds I'm going to do that. I want to keep heap execution off of the heap. I want to keep that out of the critical code path. And here, step at elapsed. I thought I was using step at run here. This is not a fair test. Where do I use step at elapsed? So NW. Dash N tells grep to put the line number out, and dash W says this pattern is the whole word, and F says this is a literal string, not a regular expression. And there we go. So step at elapsed is used just in step at. Is this a pure benchmarking function? I remember I created step at by copying step. I had step elapsed, which is what I'm really using for benchmarking. Let's see if that's true. Step elapsed, yeah, step elapsed is already used in subs for doing benchmarking. I don't really have a step at elapsed. I believe. Yeah. What I want to do is I want to use step elapsed for all of my stuff, because we don't want to repeatedly be setting that. What we're testing here is the step at init, or is this call here. And I think I'm going to continue this idea of refactoring. Step elapsed. Let's make sure make sure it's working. Haha. Okay, and T0 is no longer used. There we go. Okay, so we're going to have a common benchmarking thing, but instead of passing this benchmark a step, I'm going to pass the function and the argument, which means my benchmark code does not need to construct a step to do this. And in fact, this is looking more and more like step elapsed will become RTC elapsed. Yes, let's refactor that now. So step elapsed is going away. It's going over into support.c, actually going into rtc.c. And it's going to be used during benchmarking, so I can put it down here at the bottom below the benchmarking thing. And this is RTC elapsed of a, I'm going to just say, does RTC get to know about the step function? No, it doesn't. So this is really void star func and void star arg. So RTC elapsed is the new the new thing, and I'm having to do the declaration this way because I want to pass in a pointer, but RTC is more fundamental than func. It's more fundamental than the step stuff. I don't want RTC depending on step. So RTC does not have its own header file, does it? No, it doesn't. So one of the reasons why I start sequestering my header files, my source files into subdirectories is so when I look at the list of files like this, I don't have this big long list. I'm saying I'm looking for the header file for RTC. I just can look at the header files and say, oh, there's no RTC there. So this was supposed to get shorter. Interesting. Okay. So debug support, benchmarking support. Here we go. Extendable RTC elapsed. I am going to, at this point, say type def bench fn void bench fn bench star. Just to make it a little clearer. And pound define RTC elapsed, because I need to put that cast in. Don't need that set of parentheses there. Okay, so now everywhere that I was using step elapsed, I can now use RTC elapsed to pass it the function name and the pointer, and it will do all the right casting and all of that to get me into RTC elapsed. And now we can go through here. We no longer have step elapsed. Okay, that makes sense. So now I have that. If I were super duper clever and I would set this up as a vararg, a variadic macro. So I'd take a function and all of its arguments. And then I would set up the other one as a variadic function, which would unpack all the arguments and then efficiently call the function those arguments over and over again. However, that would only work if the function I was calling took variadic arguments. Because you can't pass on the varargs and have it land properly in an arbitrary function which may have been set up. It may be has an argument list that normally some of the arguments are in memory, and normally some of the arguments are in registers. And varargs has to strip them all out into a memory array of some length, which you then scan based on knowing what the type of the arguments are. So couldn't really, yeah, I was going to say if I was clever, I'd make this variadic, but I'm not clever enough to work around the fact that every ABI, application binary interface in C, is slightly different. Okay, so we've got that. We've refactored out our step elapsed, and we notice that we are back to running and passing all of our tests. And just for fun, I'm going to look through here And we'll look really quickly and see if anybody is still calling the old elapsed. Step benchmark is calling RTC elapsed of that function. Step at is calling RTC elapsed. Bench is calling RTC elapsed. Support has just the support stuff. Yeah, okay, we're good. And again, let's take this bit of refactoring and toss it in Git. So we've modified all these files with small mods. Okay, so we put RTC elapsed in here in rtc.c. For some reason, that line and that line are not being recognized as the same line. Oh, I bet you I have a weirdness in step.c. Oh, look at what it did. There's a blank line, so it matched the blank line in preference to matching the text. So let's put a comment in here. Step run all step, run this one step. Let's make it clear that we're receiving a reference to it. Generally what we're getting passed to us is somebody will pass to us the array. Okay, often. Sometimes they will pass to us an array plus an offset. So yeah, what we get is a pointer, but it's a non-null pointer. So if I do the diff now, and I have set this up so that diff will preferentially say, oh, we've added the comments. There we go. So that diff is easier to read. We have minused out the step elapsed. We have eliminated this bench step thing that we're building in favor of RTC elapsed. Remove the declaration. Remove T0, this bench step at. Yeah, these are all small simplifications. And this includes our refactoring of subs. So because I want to put a larger comment in here, this is going to be a little weird. Git commit. Now this put me in VI inside of the shell. Git commit -m. And now I'm going to have to put my commit message in quoted carefully. Refactor to refactorings. Oh, and the title, I really want to have the title standalone. So this is refactor elapsed and the other important thing I can name to say what this is this is subs extend. Okay, so 2 refactorings. It really wants to put that at the bottom of the screen, doesn't it? So the one is move and I want to look at it while I'm doing it. Move step elapsed to be RTC elapsed. RTC elapsed takes func ptr and arg not step pointer. This is really just two. There's going to be multiple bullet points in here. That's all right. And because this is, I'm actually typing to the input to the shell. This is not an editor window here on the left, even though I'm in an editor window in a shell. And the other one was subs extend. Pull subs list extension out to new subroutine. Subs has bubbles as recognized. This entry is not yet valid. I believe that covers what I did with bubble. In some contexts, in some projects, at this point I would be asked to break this commit up into two commits, one to do the RTC elapsed thing and one to do the subs extend thing. But I think that this size of commit isn't too big, although this is on the edge. So go back over here. Let's bring up our normal thingy. There. I think that's all the refactoring I want to do. So at 45 minutes into the stream, I can finally start on the real code I wanted to build, which is our heap. Deep breath. This is called a Sched. Okay. Pragma once. Actually, what I'm going to do here is I'm going to import the subs.h and heap.h, and we're going to change subs to Sched because the heap that we're going to be doing is going to be very similar to a subs. It's got a pool of steps, which is called I'm going to call that heap. The pool itself has a capacity. We've got a length, which is the number of entries in heap that are somehow valid. We've got a bubble. If there's a bubble in it, it's counted in len and counted in capacity, but it's not invariant checked, just like before. So, sched invar, sched init, sched add. Well, sched, we're actually going to be doing, hold on, this is a step at, because as we execute things from the heap, they execute at a specific time. So sched add is going to need a time. So at here, and sched add will take a tau, so we're going to do that. This line is getting long, so let's put a backslash in here and break it up a little bit. Sched add takes a tau there. Now, running the schedule, we're going to be able to run one and run all. So run one will consume the next item on the schedule to run, and there may be several items. Basically, what we want to do is run the item from the schedule, the step at from the schedule, whose time is minimum. Okay? And if there's several of those, we'll just pick one. And the way we'll do that is we will keep that heap area. If there's a hint there in the name, it's going to be a heap, which means that the head is at 0, and we have a parent-child relationship so that the parent at 0 has children at 1 and 2. And the invariant is that the parent does not execute after. So the at value for 0 is going to be less than or equal to the at values in 1 or 2. We are not enforcing an order between 1 and 2. Likewise, 1 has children at 3 and 4, and it executes not after them. So it's either before or the same as. So there's our invariant. Now, if we've got a bubble, it just means that when we're doing all that checking, you don't do any check that involves the contents of the bubble. The contents of the bubble it's a hole. And in fact, because it's a hole, it might very well be that our invariance, there may be no value that can be put in that hole that would satisfy the invariance. If that exists, then it's the responsibility of whatever code is moving that hole around to assure that once it's moved the hole up or down, what it's left with, everybody meets their invariance. So sched add adds to the schedule. We run one, we run all, we have all of those. So there's sched.h. And we need step at, like that. Now sched.ski, let's pull in subs.c and change subs to sched and change step to step at, like that. Now, this is not quite right. Let's go through this. Before I save it, I'm going to go through and make annotations on what I want to fix. This is to do, check, heap, order, invariance. We still have list, cap, len, and bubble being checked. We haven't added any fields. We have, however, changed the name list to heap. So we need to do that. I almost forgot to do that. Okay. So this is the correct scheduler init. Now add is going to do something worse. Basically, we're going to extend the heap by 1, and we're going to put the new thing at the end. Okay. And once we have done that, to do bubble the new thing from the tail toward the head. So it's a heap, which means we've added something at the end. We want to look at its parent. If the new thing has to happen before the parent, I want to swap them. Now, in reality, what I'm going to do is I'm going to avoid writing to slot. But the way we do that is I'm going to bubble here. So we're going to have a bubble in the place we're going to write, and we're going to compare the thing we're about to write with the thing in the bubble. Okay, so we'll talk about the bubbling later on, but basically we're going to avoid writing one thing. So instead of swapping two things, we're going to be moving the parent to the child and then switching our slot to the parent slot, and repeat that until we find the right slot to write in. Now, sched run, okay, this is early sched run 1 and sched run all. These are not critical path functions. To do repeatedly run sched run 1. So while not empty, oh, let's just write this. So run 1 says, while s arrow len is greater than 0, sched run 1 of s. To do, run the step at the head of the heap. To do, remove, let's see, let's just do this. So we're going to say this is step at run s arrow heap sub 0. So we now have a bubble at 0. And what to do, move the bubble from head to tail, to do with bubble at tail, reduce len. and cancel bubble. So we'll have to satisfy those to-dos before this will function. But that's what we intend for it to do. Sched extend is entirely unchanged. If we're going to extend it, we can't have a bubble. We do the same logic for making it longer, change the length, set the bubble to the new slot, check the invariance, and return the new slot. So our caller will get back the slot number of a bubble, and it's up to it to move that bubble around until it finds the right place to put the data that it's writing. Okay, Sched post. We are not going to have any of this to start with because the Sched testing is going to be very different from the list testing. Very, very different. Okay. So now we've got all this set up, and I believe I can, at this point, actually attach it to main. So we can add Sched to our list. So this is actually crying out for some sort of list that the modules themselves extend. So where we find a step at, we do that. Unfortunately, we can't do something in C that I'd like to do. In C++, you can include a variable in a source file that's static and gets initialized to the result of calling a function. And then you can write that function. And now when you start the program, it'll automatically run that program in order to initialize that variable. So we have now added our Sched to main. And now there it is. Okay, let's see. What's it saying? Step in var. This is step at in var. And step at FP doesn't exist. And step at AP is step AP. Sched at, this needs to have a tau at. And step at run s heap 0. This is really just s heap plus 0 because heap is an array of the structure itself rather than an array of arrays of the structure. So when we run steps, we just do that. And there we go. We are running again. We aren't actually executing any code because we've got all these to-dos and our tests are empty. But this all compiles now, and it is a first shot at adjusting the subscription list to be the heap. There was a comment about critical path in subs.c that was inside the function. Here. I want to make that a subs run s run all steps in the subs list. There we go. And so at this point, I could check in the initial I'll call it the initial cloned own of subs. I should be working in a feature branch at this point. Yeah, I think I will. So git checkout -b feature /sched. Okay. I'm going to pop out into a separate window to adjust the I'm going to push my local trunk back, and that's easier to do in a separate chapter tool. What do we want to do? Let's see. So I want to, oh, this is actually the right place for it, because what we've checked into trunk so far includes subs, step at, indenting for the 80 column limit, and refactoring. Okay, those are all things I should have done in small branches and integrated, but it's okay if they're all in this one linear trunk. I'm willing to accept that. And I just realized that I didn't push subs and step at out to GitHub yet. So I'm going to try to remember at the end of this session to update GitHub. But yeah, we are now on a feature called Sched. And I could use a branching scheme that we now use commonly in Git called Git flow. I like it for large projects because you can have a branch that represents what we have deployed to production or what we have sold to customers. You can have another branch, which is the current development branch. Okay. When you're getting close to the end of a release, you can fork from the head of the development branch, whatever you want to be in that release, you can fork off into a release branch. You've got development going. You've got 4 teams working on various parts of this huge system. Let's say this is a operating system or a compiler. You've got multiple teams working in different areas of it, so they would check out a branch in which they do their work, and when they're ready to publish it back to larger group, they would integrate it. Individuals might create branches where they do an assignment that might take them several days to work on, and they would make a branch to test that in. And when they're done, they would check that back into the groups branch. So you can, this is actually a modification of Git flow. Git flow is in some ways too big for many projects and in other ways too small for some projects, which means it is an idea that you tune to what you're using. So here I'm using some of the ideas from Git flow. I'm using this name of this branch to say I'm working on a feature called Sched. I will not be using PRs on GitHub yet. At some point, if we end up with a really huge simulation and I'm running simulating multiple different kinds of systems in different things, I will start using Git flow more strictly. I will start doing PRs. And I will be reviewing those PRs before I integrate them. But for now, I'm accepting this, and trunk is there, and we are good. We may or may not, this may or may not show up as a merge, okay? So, but we started on feature Sched, and I'm going to git status. This says that I have modified main and subs, and I have untracked there. So git diff we need to pipe it to cat. I've got some fancy stuff to post-process the git diffs, which works great in a terminal window, and it doesn't work so great when I'm inside the Emacs editor window because it really, really wants to show me things. I mean, it doesn't do a bad job here, but it is not optimal. Whereas if I tell git diff I'm sending the output through a pipeline, it'll just do it in plain ASCII. This is really what I want to see. So main has my Sched added, and subs.c had this. This is trivial. I don't need to mention it. Git add dot, git commit dash m, clone to own subs into Sched. Clone to own is a term that I didn't learn until the early 2000s. It was a term that was in use at NASA because at the time, most spacecraft missions, you would find a mission that had similar hardware, similar avionics, and you would clone their project. Now, they ran their mission, they got their code working, they ran their mission, maybe there's some bugs in the code they never hit, and they're done. literally the software engineering team for that mission no longer exists, but the code still exists. So you're on a new mission, you go and you find their code in their repository and you clone it. Now, this is a term that was in use even when we were using stuff that wasn't Git yet. And then you would own it. You own the copy, and you start modifying that copy to match your mission, and you debug the things in the code that don't work in your mission, or the things that worked by accident in their mission, or corner cases they never hit. Anyway, you polish it more further. Now, as code moves from project to project, it gets a little better each time. So this is not a bad way of doing things. It works really well. It's not the best way, which is why we gathered a bunch of people together in one particular case and took a bit of code that everybody had been cloning to own. In some cases, multiple projects owning their own copy of it at the same time. And we tried to kind of pull it together centrally so that each person, as they were making changes, it would go back in the main repository and the other projects would be able to pull it if they wanted it. And then in the future, when you want to do a clone to own, instead, you got a copy of this thing from the central repository. Look that up, that's CFS. Project near and dear to my heart. And if there's one thing I regret about leaving NASA, it's that I stopped working on CFS. It was a joy to work on because there were some really, really, really smart people working on it. I mean, for the first half of my career, I was accustomed to being the smartest person in the room. Now, part of that is because I was an egotistical little bastard. And part of that was that some of the people around me were telling me I was the smartest person in the world, right, in the room. And part of that was that as I met some of the people who should have been the smartest person in the world, I won't name any names, but there are some people who are famous for doing excellent engineering. And behind the scenes, there are teams of people at the company that are trying to eliminate every bit of code they wrote because what they wrote was trash code that happened to work. I mean, it got it working, but it was like, oh God, who wants to maintain this? Anyway, so there I was, massive ego, being told I'm really, really talented. I didn't hear the subtext of for someone as young as you are. And debugging and fixing code that had been written by people that should have been smarter than me, and I was fixing their code. So I was used to being the smartest person in the room. So I land at NASA. And I look around. And everybody is smarter than me. These are amazing people. I mean it. I landed at NASA Ames research facility. And in my specific field of expertise, I was better than most people around me that weren't in that field of expertise. However, not by much. I mean, you've got people that their area of expertise is aerodynamics. And yet, you know, they sit down and there's a bunch of Fortran code and they can just hammer that shit into shape. I mean, make it work, make it do what they want to do, make it work fast. I come in, I can make it a little bit faster. I maybe can add features to it a little faster than they can. But these are excellent engineers, even though engineering isn't their field. And I worked for Karen Gundy Burlett. Shout out if you're seeing this. I think smartest person I've ever worked for or with. And it's like every few years, completely different project in a completely different field. And she knew what was going on. It's like, this is an excellent idea. Let's try this. And it works. And then something completely different in a few years. And wow, just amazing, amazing people. Anyway, so that's NASA. So yeah, I'm not sure where I was going with that, but yeah, I was not the smartest person in the world when I got there. Anyway, so clone to own. Oh, all right. I was just saying how much of a joy it was to work on CFS because all the people in the room were just so amazingly smart. So we are now going to commit this clone to own subs into Sched. And I'm not going to push it or anything. We're just going to keep working. So where are we here? We have no tests. We have several to-dos in here, and we have established that we have a storage area for a bunch of step-ats, which has a capacity, it has a current length which is not greater than the capacity, and it may have a bubble in the middle where we want to ignore the invariance. Let's look at what the invariants we want to have are. So, heap invariance. Entry 0 is the next thing to do. Entry 0 has children 1 and 2. Entry 1 has children at 3 and 4. 2 has children at 5 and 6, etc. I like writing these out as comments first so I can figure out the best way to test them. Given a entry I, the invariant is that its at is not less than its parent's at. Okay, so instead of saying I'm looking at the parent, compare myself to both children, I'm going to say I'm looking at the child, compare myself to the unique parent. So now we're going to check the invariance for, okay, so we're looking at I. I is going to step through them all. So we're going to say int parent p is equal to, and we see that 1 and 2 we're going to go to 0. So this is I minus 1 over 2. Now, if we used 1-based indexing, 1 would be children 2 and 3, 2 would be children 4 and 5. So we'd be able to say your parent is half of yours. I have to subtract 1 to get to the right parent. So now if p is equal to, so it's actually not a problem if this is 0. This is going to come back with a p equals 0, but I don't want to actually do that. So if I is equal to 0 or return, continue. If I is equal to 0, we don't have a parent, so we're done checking the invariance on this thing. So there's p. If p is equal to bubble, continue. So if our parent is the bubble, we don't want to do the comparison. So now we assert that s arrow list sub I dot at is greater than equal to s arrow list sub p dot at. There we go. And that handles our ordering constraint in the heap invariance. So where's my to-do on my bubbles? I thought I left to-dos. Oh no, I'm in the wrong file. Okay. And that's why you leave to-dos, so you know that you're in the right file. Hold on, git diff. Okay, so we only have the one file changed. Get my build loop going again. So here, list is actually called heap. Now doing all these things with heap, how about instead I start int, let's see, let's actually grab data from the structure here. So assert s before we start snapping, but then we can start looking at things. So cap equals s arrow cap. So if we have an S, then we can look at all the fields. Like that. There we go. So ordering is now checked for Sched. Not subs, Sched. Okay, Sched add. So here, we have bubble new thing from the tail to the head. Well, instead of writing a whole bunch of code in the middle of this function, we already have a thing here where we say Sched extend slot. What I'm going to do is I'm going to do it right here. So after we determine our slot number, the bubble could have been anywhere. So S arrow bubble, well, slot. Am I going to assert that Sched extend sets the bubble to the slot? Yes, I'm going to do that. In fact, let's do that here. Assert S slot equals S arrow bubble. Someone broke Sched extend bubble is not bubble not equal to slot. And this is S arrow bubble. Okay. That's better. So if we ever break extend so that it's not setting the bubble to the slot it returns, well, it's returning to us a slot that we're supposed to be able to write in. And that slot needs to be in the bounds of the heap. And it needs to have data in it that we don't care about, so it's got to be the bubble. So we're going to assert right there. That's the bubble. And if somebody breaks that, I want to know right away. So we could have either picked up the slot from the bubble here. And in this case, what I want to do is I don't want to set the bubble to -1 because we haven't written to the slot yet. In fact, that means that we are setting bubble to -1 too soon in the other code. So this is in subs.c. So subs add is setting bubble to -1 early. So this is if slot less than 0 or slot greater than equal to slen. So if slot's out of bounds, then we extend to get the new slot. We don't muss with bubble until down here. There we go. A lot of these invars will go away eventually, but right now they are local paranoia. Subs add is not going to assume that subs extend checks invariance at the top and bottom. We're going to check it again when we get to here. When this is tuned, when we start optimizing, most, if not all, of these invariant checks are going to go away. I'm going to leave the ones in where potentially something else could reach in and corrupt the state of subs. Same thing here. There we go. Didn't break anything. Good. So instead of writing code inside Sched add, I'm going to call a function. This is Sched bubble to tail. But we want to stop when we reach the tau value. So we call this bubble, we say bubble ink. can't think of a good name. This is going to say, starting at the bubble, I'm going to pass in the slot number. Rather than having, call that Sched push. So Sched push says, starting at this slot number with this at, move us down the heap toward increase, push us down toward the tail. Sched to tail, that's even better. Move toward the tail until we, if we need to, because a child is newer than at. This is actually the more complicated of the two. There's actually a Sched to head, which we'll use when we start with something at the end and we move it toward the, where the bubble is at the end, and we need to move the bubble up. And yeah. So when we, hold on. No. This is add. So we are potentially starting with the end slot bubble Sched to head. We're actually pushing the bubble toward the head here. Oh, I almost messed up royally. So we have added something. Typically, we have appended it to the end of the heap, or we have inserted an existing bubble. We need to move it toward the head. If the bubble is at the head, oh, that's a bug in my prior bubble sort thing. Okay, I have two cases here. Really. I'm inserting the new thing in the head element, in which case we want to move toward the tail. Or I'm inserting it at the tail, in which case we want to move toward the head. Or I'm inserting it in the middle. Now, when would bubble be in the middle? Well, bubble's only in the middle if we are in the middle of moving it. So what I'm going to do is I'm going to say Sched literally at this point we can go either way. So Sched extend, I'll put it up here. So if slot is less than 0, if slot's less than 0, then we didn't have a bubble. Now I face the case of what if slot is equal to len? I think I'm going to have to be more strict about this. I'm going to say that bubble can be anything when we go into invar, but coming into Sched add and so on. So Sched add, we either have no bubble, or we have a bubble at 0. Assert slot equals -1 or slot equals 0. So if slot less than 0, else. Okay. So if slot is -1, then we didn't have a bubble, so we're going to extend. If we did have a bubble, I'm going to say assert slot is equal to 0. Sched add, if bubble exists, must be at 0, not at %d. Bubble us from slot at end toward head. And I'm going to also assert slot is equal to s arrow len -1. Slot %d is not 1 less than len %d. let's call this len. This is last. Is slot is not equal to last. So if I extend it, I'm going to assert that slot is equal to the last one and it's equal to bubble. And the to-do is slot at head toward tail. At tail, there. So there's our assertions, and we are being tighter on our constraints about S bubble. And this Sched underscore goes away because we are going to push to tail S slot at, and this is going to be Sched push to head. And these are both going to be static functions. So let's set those up. Oh, and I forgot to type. So types here are Sched, S, int, slot, and tau add. And what I want to return is the final slot number, like that. Let's go fix up the declarations again. Okay. They're not doing their job, but they now exist. So how does this read? Add says bubble. If we don't have a bubble, extend and push from tail toward head. If we do have a bubble, it's got to be at 0, and we push from head toward tail using this add. And we do a Sched invar. I'm going to push the Sched invars into here. So if Sched invar notes a failure, I can get a stack traceback that says whether I was in push to head or push to tail before we failed. Okay. So before I get too far into this, we don't actually have any of this code being run. Potentially a bad idea. Almost forgot. We need the revised slot number from the push. And when we're done, we are going to then write into that place. So aside from the asserts, this is now small code. If I were to wipe out the asserts, it would look like that. So later on, if I peel this down to minimum, remove the asserts, remove the Sched invars, this becomes a very simple slot. We do that assignment, we push to head, else we push to tail, we're good. So run one. Goodness, we have another case where we are move the bubble from head to tail. We want to do the same thing. We want to push to tail. So we want to start at the bubble, which is at 0. Oh, the other thing I need to make sure is that these guys need to reset bubble. Oh, no, they don't. They need to move bubble. And when I write slot, yeah, that'll take care of it here. So when I write new data in the slot, I say if the slot was the bubble, then the bubble is gone. So I pop the bubble. Slot equals push tail there. And then and at is going to be tau max. Please tell me I built tau max. If not, it's time to do it. We are going, this should, with tau max, this should push us all the way out to the tail. If it doesn't push us to the tail, I'm going to assert fail, because that would happen if somebody else pushed something onto the schedule, scheduled to happen at tau max. Oh, let's fix that. Okay, so sched add, I'm going to say assert at is less than tau max. Sched add, adding a scheduled event at tau max is not allowed. There. So now I know that I won't be adding any events to the schedule that are at tau max. So I can use tau max as the at value that will force the bubble all the way out to the end. So this slot should be equal to s arrow len minus 1. Okay, and let's do an invariant check when we get back from that. And we're going to then say s arrow len equals slot. So we trim it off the end. S arrow bubble is equal to minus 1. Pop the bubble like that. So when we get back from there, the bubble and the slot should, the slot it returns and the bubble should be at the end of the thing. We trim the end by 1 down to slot number. We do that. We say sched in, check the invariant, cancel the bubble, and that's done. So run 1 does all that logic. So this push to tail thing, push to head and push to tail, they are order log n, where n is the number of things in the heap. And that means I'm actually going to be looping, number of times I loop is log base 2 of n, rounded, truncated down, maximum. So it will depend on whether I go left or right as I move down toward the tail. And going forward, no, log 2 rounded up, going upward. Okay. So potentially, yeah, it's order log n. Okay, so we come back, we assert that we're stable, we assert that our state is what we expect, we adjust counters, and we check the invariance again. And because I am totally paranoid, I am going to do this. So sched run 1 gets corrupted and returns us a sched that doesn't have its invariance set, then we're done. Okay, so I called the macro with not enough parameters. Come on. There. So slot in run 1, push, could not push bubble, did not push to tail, did not return last slot, and run 1, push to tail, did not set bubble to last to tail. I could put a special case and push to tail, but I'd rather not slow it down. The special case would be if I'm pushing tau max, don't compare it with anything, just always put it all the way out to the far end. So tau max would be essentially infinite time, and we would always push to the very tail. Okay, run all. Sched extend does not change. Push to head. Okay, so we are an hour and a half into the stream, and we are finally getting to the two pieces of complicated logic for the heap. Those of you who have a standard education in computer science know what a heap is. We've mentioned it before when I went over the invariants. Those of you who are self-taught or interested or not formally trained may not know what a heap is. Basically, it's a collection of things where we can always grab the one we want. Always grab the one, in this case, with the lowest value in the scheduled time. And the way you do that is, if you look at any element within the heap, it is not after its children. So any node is a parent to two children. And it says, well, okay, run me before you run either child. The child add double my index plus 1 and double my index plus 2. So we have a bubble in our heap, a place we're going to store something. And we want to move that place around until it's appropriate to store this scheduled time. We're pushing toward the head. So while slot is greater than 0, and I'm going to be paranoid, assert. So we get to here, I want to assert that slot is equal to S arrow bubble. Loop invariant failed, slot %d not equal to bubble. Okay. So what we want to do is look toward the head, which is the parent. So int p is equal to slot minus 1 over 2. So parent 0 has children 1, 2. Parent at 1 has children at 3, 4, etc. So slot minus 1 divided by 2. So 3 minus 1 divided by 2 is 1. 4 minus 1 is 3 divided by 2, round down, truncate down is 1. So that's good. So that gets us P as our parent. So under what conditions do we want to exchange the parent and this child? Well, if at is less than sched arrow heap sub P dot at. More importantly, we want to terminate with the reverse of that. So if our ordering, if at is okay to be here relative to that parent, we can break out of the loop. Okay. Otherwise, we need to exchange. So the way we do that is S arrow heap sub slot equals S arrow heap sub P. Structure assignment. And then we are going to say slot equals S is parent. And we're also going to move the bubble. And because I am totally paranoid, I'm going to check the invariance again at that location in the loop, like that. And the reason why I'm checking the invariance is we have moved data in the heap. So whatever was in parent is now in the candidate slot we had. I want to check its invariance relative to its new children. It has now moved into a new slot. It's got new children. Let's compare them. And the easiest way is just to compare all the invariants. Total overkill. So in each case, slot is greater than 0, and p is going to be less than slot. Okay, so it's slot minus 1 divided by 2. If we just divided by 2, slot of 0 goes in, slot of 0 comes out, it would be equal, and we wouldn't make any progress. But if slot is positive, this makes progress towards 0. And when we leave the loop, we have a position where we do not have a parent that happens after us. And we can return slot. Okay, there's that. Now, moving the other way is a little more tricky. Well, before we do that, I am going to set up some temporary variables here to make this faster. Int bubble equals s arrow bubble. And p step at heap equals s arrow heap. And bubble, bubble, heap, heap, heap. So we're going to keep bubble, well, I have all sorts of assert bubble equals heap in there, don't I? So slot equals bubble. If I'm going to do that, yeah, okay. I do need to store it back in bubble because I'm hitting Sched in var. If I didn't do the invariant checks here, if I allowed myself to violate the invariance, I could move the bubble all at once down here. More importantly, if I was really, really worried about performance, I would elide moving the bubble completely, and I would say when Sched pushed ahead of returns, it's the responsibility of my caller. But then I wouldn't be able to check invariance on return from this function. So I want this function to return with Sched set back so its invariance pass. So we do need to update the bubble at least once. If we have to optimize this routine, that's one of the things I'll look at. Okay, push to tail. We are going to be comparing with, we're going to be looking at the heap. We are going to be looking at int len equals s arrow len. We have a slot, we have the bubble, so while slot is less than len. So because we will be stepping from a parent down to a child, this means we are going to be doubling it each time, double plus 1, double plus 2, and we're going to need to break before we look at the parent. So this is just a while one. This is a forever loop. And what we want to do is I want to look at the parents. I want to look at the children. So we have at, so we need to say int c equals parent at 0 has children at 1, 2. I should just leave this written up somewhere. Now, I talked about this as being old school engineering. Actually, if I was doing this as a paid job, if I was back at Sun working inside the kernel, I wouldn't be doing all of this with such small, careful steps. A lot of this, I would like have some handwritten notes. I would have things like this handwritten notes, and I would just be blasting out the code and minimal testing to make sure it works, because that's all I really need. I probably wouldn't write the invariants because there is such a thing as proof by inspection. You can look at the code, you can say, I can see that this code always does this, and it's 3 lines of code, and we're done. And I wouldn't write the invariants, and I would put a comment in somewhere that says this is what this code is supposed to do. Now, that's what comments are for. Comments don't say what you're doing, they say why you're doing it. And I would count on my fellow professionals to not muck with a function in such a way that it stopped doing what it was supposed to be doing. Now, because of this, this is where bugs come from. It's where 2 people have different understandings of what code is supposed to do. So person A writes the code and says it's supposed to do X, and person B reads the code and modifies it thinking it was supposed to do X prime. And X prime is slightly different from X in a way that some bit of code elsewhere in the system is sensitive to. That's where you get bugs. But if I were to work at this level of granularity, I mean, I'm working very slowly and writing very small things here, I would not have gotten things done fast enough to suit my managers, and it wouldn't have suited me either. Anyway, so parent. So first child is going to be at 2p plus 1, so 2 times slot plus 1. If c is greater than or equal to len, then we are done. Okay, if our first parent is off the end of the heap, then we're at the right place. Oh, also because I am working the bubble, loop invariant failed, slot not equal to bubble. Okay. So if that's true, then what we're going to say is, I am going to say int c at, this is actually child 1, but we'll call it child. CA for child at is equal to heap arrow sub c dot at. Okay. Now, there may be more than one child. If there was only one child, we'd compare CA to at and we'd be done. But there might be more than one. Int C2 is equal to C plus 1. Look at the next child. If C2 is less than len, we need to consider the possibility that the second child is before the first child. So C2a is heap of C2 at. Now, if C2a is less than C2, CA, so if the second child should happen before the first child, then we want to consider the second child for swapping with the bubble. So at this point, we would say C equals C2 and CA equals C2A. Okay. Consider the first child. Or maybe the second child if it should run before the first. So if at is less than or equal to CA, so remember CA is which is the at for whichever child is supposed to run first, then we're done. We can break. Requested at is not after either child. We are done. Have found our slot. Otherwise, we need to move to the child. And that is exactly this, except instead of P, instead of moving to the parent, we are moving to the child C. So get down to here, and coming off the end of push to tail, literally slot matches bubble, but they could be anywhere in the heap because they are further down the heap than things that should happen before us, and not further down than the children that should not happen before us. So get down to the bottom, and I think, yeah, we're done. So if we wanted to not assert our invariant about the bubble, then we would not update bubble until the end. That's an optimization we can make. We do have to move slot. come back up to the top. Are we guaranteed that slot makes progress? Well, let's see. C is going to be double slot plus 1. Even if slot is 0, C is still greater. We might change C here to that plus another one, so that's still greater, so we're making progress. We know that we are not moving forward. Okay, so if our child would go past the length, we're going to break. So we're done if our children are off the end. So there's our termination. We're done if the children are not before us. Otherwise, we step to the child. That makes progress. So this assignment assures we make progress forward. So the new slot is greater than the old slot. So if we're looping back, we're always making forward progress through the heap. We're roughly doubling our index every time. So our move forward is order log n, where n is the length. So this loop should terminate. Proof by inspection. Okay. Testing it. Ignoring the implementation. Looking over here at the things we have defined. I can add things to the schedule, which are at a certain time call a function with a parameter. I can run one thing from the schedule, and I can run the schedule until it is empty. So, power on self-test. We're going to make a schedule. Sched s, sched init of s, and sched invar of s. My test is not going to assume that init tests the invariant. Hold on, print top. Let's pop this in everywhere. Bist also is going to need one. And bench is going to need one, but I'm not testing anything in bench, I'm measuring. And now if we let it run, we do indeed see that we are printing those things to the log, so we are being called. I'm going to leave those markers in for now so I know, when I get messages, I'll easily see in the logs where that's coming from. So what is the first thing we need to do? I need to verify that I can call sched add and then watch as it executes it once. Oh, sched run 1. What do I do if it's empty in sched run 1? So if it's empty, we return 1. Step at run heap 0. Bubble equals 0, so we've done that, and we're in var. What if bubble's already 0? Okay, there's optimizations we can do here. Not just optimizations. We are calling an external function here which may insert data into the heap. So I need to set the bubble to 0, verify the invariant. Risky. We assert that setting bubble and testing invariant do not change contents of the heap. Cell that is the bubble. So we still need to have the actual data in that cell needs to not change throughout this process. So sched run 1, we have the additional problem of what if bubble is already set to 0? What if we don't have data at 0? Okay, so there's this idea that we can inside the function call, we may schedule something onto the schedule again. In fact, we probably will. most of our events may reoccur. So Sched push to tail. At this point, when we come back, yes, more to the point, hold on. If we still have a bubble at 0, we don't want to do the rest of this crap until we need to. So I'm going to invert the ordering a little bit. This is even before we start testing, guys. So if S arrow bubble not equal to -1. If we have a if we have a bubble, we have to get rid of the bubble. Okay? So if we have a bubble, we need to push it to the tail and reduce the size. So that's where all of this logic goes. So we have a bubble, so we want to push to tail. We want to start at S arrow bubble and push that down so that we push the bubble out of the heap, so we know that our 0 element is good. And we know that we can set the bubble to 0. If the bubble's in the middle of the heap, we could still execute the guy at 0, but then we'd have 2 bubbles in the heap. Oops. Also, we have the problem that if there's a bubble in the middle of the heap, maybe one of the children of the bubble is actually belonging at 0. I believe this can't happen. Yeah, because if it could happen, it means a bubble in the middle of the heap, we would have to push it down, and then we'd have to take the guy we bubbled up and bubble that all the way up. So I believe that all of our bubble instantiations are start at the front or at the head or the tail, and then move to a proper place and go away. So our invariant for user calls is going to be the bubble is either non-existent or the head. So here we say, if bubble is not equal to -1, then move the bubble. More importantly, if the bubble was 0 and the length was 1, we're done. So yeah, we could end up in run 1 with a heap that has a bubble in 0 and nothing else. And this is the path we would take. We would push to tail from 0 to the length, which is 0. You would return a 0 slot. Slot would be len -1 because len is 1. And bubble is 0, len would get 0, bubble would get -1, and we would return. Okay, so now we have a heap without a bubble. We put the bubble in 0, and we check its invariance, and then we run the thing. And when the thing is done running, we assert that the invariants are still set, but we've already done all of this. Okay, and it's okay for run 1 to return with a bubble at the head. Because typically, we're either going to have done something here. Now, step at run could insert something into the heap. If so, it lands in that insertion. So we're running this thing, we put the bubble at 0, we start running the code, and it does a add. Well, the add is going to put that thing in the 0 location and bubble it out, and we're going to end up with no bubble in the heap after we've done the insert. If it doesn't, then we're going to come back from run 1 with a bubble in 0 and the same length. And the next call, we will then run the bubble out here, and we're done. But we don't run the bubble out until we have to, so we're going to be lazy about moving the bubble. And that goes with what we were doing in add, which said that if we enter sched add with a bubble here, then we simply push the bubble to the tail until we get to the appropriate insertion point toward the tail to get to our point, and we write it. So that will save us from doing repeatedly decrementing len and incrementing len and decrementing len and incrementing len with all this movement. So that also reduces the amount of bubble movement we do, because we don't put the bubble at 0, push it out to the end, and then put the bubble at the end and push it up to the middle. Instead, we just put the bubble at 0 and then we push it to the middle, and put the bubble at 0 and push it to the middle. I believe that's got it for us. Sched run 1 says if we have a bubble, then do something about the bubble. Come down here, set the bubble to 0. Run all says repeatedly run 1, extend, push to head. Push to tail. Okay. Still no errors. Good. I'm making my window a little bit bigger there above my head. I think I'm going to make the camera smaller because I want to see more output. And the little window behind my head, I'm just gonna have random crap in there that doesn't matter. So, going back to here. Now that we have our digression into optimization for the day, Sched post runs, it creates a Sched, it verifies the invariance, and it does it. When we start removing invariant checks, we'll remove it from a lot of the code, but we won't remove it from the tests. So now I'm going to Sched add of S. We have a current time tau, so I'm going to say tau plus 10, and the step function pointer is going to be Sched F1, and this is going to be counter. Int counter sub 1 is equal to I am spending a lot of effort to remove a few lines of code in one place. Counter equals 0. Address of counter. Static void Sched, I'll call this Sched inc, int star cptr. So we're going to have a job that is Sched inc inc cptr. This is going to be inc once. So he's going to increment and leave the queue. And his thing here is plus plus star cptr. Just like that. And I need to use the macro because that corrects the type. Because, of course, what we're scheduling has a void star, and what we actually have in the way of a function takes this. There we go. And for those of you that are nervous about type safety, I just got to say, it's C99 type safety. We don't need no stinking type safety. So we're going to Sched add. Now I am going to assert eq int counter is still equal to 0. Scheduling task does not run it. Now that's actually a macro, which is defined in somewhere. Assert eq integer. Yeah, I forgot. That has all of the messaging built into it. So let's do int const int counter. So this is start equals 0 int, yeah. So now, if this were to fail, how would it fail? It would fail because I'm going to initialize it to the wrong value and verify we get a failure message. And there we go. So if I initialize this to start plus 1, we're going to get assert eq integer, test condition failed, counter equal to start, expected value 1, observed value, expected value 0, observed value 1. That's good. So now I am going to run the schedule once. So Sched run 1. Now I'm going to assert that this is equal to start plus 1. And yep, we are quiet. If I compared it to start plus 2, we would get a failure here. Now I'm going to run again. Nothing should happen because this guy didn't recycle. And indeed, nothing, so this still passes. And we're going to do another Sched inc and again, repeat, inc repeat. And Sched inc repeat is similar. But Sched inc repeat will put itself back on the queue. So we're going to do Sched inc repeat. And we're going to do this. It's going to be plus 2, plus 3, plus 4, and plus 5. So the other thing I want to test, well, let's get this working first. Oh, Sched inc repeat needs more than just a counter. It needs to know what queue to put itself back on. So type def struct repeater. This is called a p rep pip ctx and what that needs to have in it, I am going to put the counter in there. So we're going to int counter, and then we're going to do Sched Q. So inside the real simulation, it is very likely we will have a singleton scheduler. So we'll have one schedule in one place that has things to run. And it would own the current time when it's running, instead of having multiple queues where sometimes I run one, sometimes the other. But for now, I'm not going to assume a singleton until I have to. So now these guys actually take prep, and these take rep ctx. So now I need to say ctx arrow counter plus plus, and this goes on to ctx arrow q. Actually, make that dash s. So now here, what I want is a rep ctx, which is equal to start, comma, s. So this tells us that I forgot a comma. Warning, initialization is struct anonymous from incompatible pointer type. So rep ctx, Sched is a array of 1, so it's not going to do that. So what we want to do is that, and Sched init of ctx arrow s. Because I up here said that rep ctx owns a scheduler. Which is okay. I will work with that. And I'm going to say CTX arrow counter will start before this sequence and again after before this sequence. And I also want to be testing the value of tau. So we go tau, T0 is equal to tau. So after this, I want to assert EQ integer T0 plus 10 tau. And it's going to stay at 10 because we're not going to do anything. T0 plus 20. So after we run one, this is at T0 plus 20. Oh, come on. I'm fumbling figuring this like crazy. 30, 40, 50, because we are rescheduling ourselves every 10. Now, what is this doing here? Sched add Sched inc once and counter. Well, we don't have counter, we have CTX. And star counter becomes CTX arrow counter. There we go. Refactoring complete, and it passes all of the tests. Now, if we were to adjust our period here to be something other than what the test expected, then we get the failure here. So we asked it to go at 20, we went at 20, it recycled itself to 31, we expected 30, so expected value 54 is T0 plus 30, observed value is 55. So we said, okay, our period was wrong. Let's put it back to the right stuff. So BIST is now set up to verify that we can run one thing. Well, this is really more, this is a BIST, not a post. We'll make BIST bigger and we'll make post smaller. So post, I need to run twice here to verify that it runs once and not the second time. I need to run twice here to verify it runs once and not runs once and twice there. Now I need to have more than one repeat. So I am going to, let's make this psched so we can have multiple of these, and I'm going to int period like that. And period won't be used by inc once, but will be used by that one. So CTX arrow period equals 10. And this is tau plus CTX. So now I can have several different scheduled calls inc repeat with different contexts, which will all reschedule themselves on the same queue, but with different periods. CTX1 and CTX2. And we now have to build our own Sched S. So what I want to do now is set up, first of all, ink once, I want to put 2 instances of it, one at 10 and one at 12. And I will put those both in the same context. So we're going to run one, and it's going to increment to 10, and increment by 1, and we're going to run one again, and it will increment to 12, and we will set it to get to start 2, and then we're going to run it again. And nothing's going to happen. Break up these big blocks of tests so that each block starts with do this and then test these things. We don't have CTX, we have CTX1 and CTX2. CTX2 isn't going to come into play until I get down here. There we go. So CTX2's period is going to be 11. Let's do something where it's going to be more obvious that we're getting some different order. Let's set it up to go 17. This is going to be T0 plus 20 and T0 plus 27. Oh, I'm not testing run all. Haha. So I need to do these again using run all to run them. So I do a run all, and it should come up with that. And this guy does a run all. It comes up with that. Now, I just got a segmentation fault. I made too many changes. Without noticing what was going on. So it's not in this code. It has to be in the stuff I did in BIST. I'm actually not seeing any output here at all. I'm not seeing my print tops at all. So bin live coding. So stop Sched post, we got to there, and haha. Okay, so this is because I changed from a Sched to a pSched and I didn't finish the refactor. That was quick and easy. So now, with that out of the way, we come down here, and of course, CTX1, this is saying, I observed 114, I expected 114, and I got 111 here. That's because, let's make sure this is 2. So, all new code. Let's start off with the post stuff and get this working, and then we'll go down to do the other stuff. So step at invar. This says we can never have a step at that is less than tau. I don't think that's a valid thing. I think a step at has a independent thing. However, it is the job of the people using step ats to verify what's going on with tau. So I am going to wipe that out. Well, that could have caught something. Hold on, let's take a look at it. Hold on, now it's not catching it. That's not good. It's looping forever. So we do indeed have a bug, and this assert caught it. So there's our traceback. All this stuff deals with doing assertion fails. So we are at step at invar line 9, sched invar, sched post. So we want to go up to frame 8. So we're checking the invariant here in sched invar. We're looking at 0. So this is the first iteration through the loop in a sched invar check. Let's take a look at S. Value has been optimized out. Okay, well, let's go up. This is sched add of CTX-S. So we are about to add something to the schedule. Probably what's happened is that we have a bubble at 0. And I am, no. I don't have a bubble at 0. Bubble is -1. We don't have a bubble. So at 0, we have an add of 34, a function pointer that points to sched once, and we have an AP. So the complaint is here that my assertion is that the SAT, we've got an SAT which is less than 0. Well, print tau. Our time is incremented to 54. Heap sub 0, which is not a bubble, still has 34 in it. Okay. So what's going on here? What's going on is I tried to schedule something in the past. So sched add needs to catch that and report it in a little bit better way. Assert AT less than tau max. However, I also want to say assert at is less than or is greater than or equal to tau, adding a scheduled event in the past. Not allowed. Requested time, current tau percent LLD. Requested tau percent LLD. And we are going to pass in at current tau is tau, requested is at. Just call this request tau. Okay. So, and that gives us a better indication of what's failing here. So instead of looping forever, we now have a thing that says, oh no, you tried to add a scheduled event in the past, and we are not going to do that. And the easy way to find this is, again, to go GDB. Abort, assert. This is where we're doing the add. So here, instead of plus 10, print, print tau, print T0. Where did my error message go? Test condition failed at greater than equal to tau. Okay, so this said I requested at 34, and my current was 54. So I just need to make sure it's T0 plus something bigger than 30. So it's going to do 40, and this is going to be at 40, and we're going to add at 50 here, and this is going to be 50 here. Okay. Amazing the errors you find when you start to actually test things out. So now our tests are running. We are correctly doing this. What I should do is after I do the run, I should reset T0. So really what I should have here is counter is equal to start, T0 equals tau, before all these Sched adds. This is T0 plus 10, 10, 10, 20. 10, 10. Is that right? Yeah. Run all. We have scheduled one thing on ink repeat. Oh, wait a minute. If this is scheduled to do a repeat, run all is going to run it forever, or it should run it forever. And indeed, live coding is running forever. So what we want to do is we want to make sure that Sched ink repeat has a termination condition. Int deadman. Actually, let's say int until. What I'm going to do here is I'm going to say if ctx arrow until, if ctx arrow counter is less than ctx arrow until, there. So now where we use period, we need to set until as well. And now this is going to be some tau value. I'm going to just tofu, trust on first use. Okay, build loop is running and it aborted. Okay, so with this says condition failed. Expected value 64, which is t plus 10. Observed value 144. Because run all of ink once. That doesn't make sense. T0 is tau. Sched add that. Sched ink once. Oh, we did the Sched ink repeat up here, and it did leave it on there. So we're going to do ink is start plus 2. Yeah, we're just going to do that. There we go. So only do it twice, so when it runs here, it will remove itself from the queue. The problem was we were entering this test case. We still had the schedule from this case. So now we run this guy. Now, if I swap the order of these, counter equals start, run one, counter equals start, run all just once. Then we're going to do the Sched ink repeat here. And I am going to run one a couple of times. And then I'm going to do a run all. We don't need to do the add. I can just check it like that. And run all, and it's going to have some value in here. So we're going to do it 10 times total. Let's do start plus 10. So this should be start plus 100. Oh, off by 1. Oh, start plus 10. Now tau, we're actually seeing 201 when we need to see 204 in that test condition. So we've been messing around in post, now we're messing around in BIST. Let's grab post and, well, let's do it side by side. Got post here, run down to BIST. So BIST should be doing more than post. This should be minimum to verify, and this should be extended out a little bit. There's not a real big difference right now. So we are doing two different things. We're going to ink once, one at 10, one at 12, and that's going to run it out. Then we're going to do the same thing again and do a all. Let's get add. Need to add them again. And now we're going to do a run all. And it should come out to there. Let's get add. In the past is not allowed. I almost forgot T0 is equal to tau. Hold on. Let's get add, boom, 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 run these guys. T0 is equal to tau here. Okay. Now I come down to here. So CTX1, sched add, CTX2, sched add. We run once. 27. And again, this is at 27 and start plus 2. This is all kind of new code over here. Let's just trim it back. And this is a abort and like 385. Okay, that's off by 1. That's not good. Okay, so this one is failing. So this is actually going to be start plus 1 on CTX2 counter. So job 1 ran, job 2 ran. And they are both different things. So job 1 comes back at 30. And 27 plus 17 is 44. So we're going to do 30 and 40. 2, 3, and 2. So here, we did not see it 30 because why? Did we see? I'm thinking that we probably saw the next execution of here. So what's happening is that we are seeing the execution of the wrong job. Which is interesting. It means that I probably didn't set up my until. Yes, that's true. CTX1 until is equal to start plus. Let's run the one with period 17 will run 10 will run 17 times, and the one with period 17 will run 10 times. Hey, Lucy. Cat saying hi. And now, there we go. Hold on. I'm going to go grab the cat. And she wants some attention. I'll be right back. You want to be picked up? Is the world awful? Come on. Okay, mandatory cat break. So now that I have the limit set in the context there, so that my test code knows when it should cycle itself and when it shouldn't, when it should reschedule and when it shouldn't, you notice that my test is now running. And as soon as I can put down the cat, we will add to the built-in self-test that we want to do a run all in both of those cases. We've done the run all for the case where we are not recycling. That's enough? Okay. She just came over to say hi. And now she's sniffing at the computer fan. I still have the computer rolled out. I get a new power supply tomorrow, which will replace the power supply that is having problems when I start drawing more power. Anyway, so now we want to do a run all. And we want to assert some things about tau and CTX1 counter and CTX2 counter. So if I just let it run, basically it's going to say that tau is going up to 308. Let's work out what it should be. So the first guy is going to run 17 times with period 10, starting at 20. So 20 plus 10 times 17 plus 20 star 10, 17 is going to be ending at 190, so tau plus 190. And we'll have increased it by 17. The other guy will have increased it by 10, and he's also at that same distance because he is, you know, he starts a little bit later. And what I'm seeing is that I was expecting T0 plus 190, and I got back 80 less than that, so I got plus 110. Hold on. So CTX1 counter is only being incremented by 10. Oh, CTX2, there we go. 190 plus 17. That test condition is now off by 1. We actually observed 10 less. Right, because the first count is at 20, not the 0th count. And there we go. We are passing our test. So there we go. BIST is now running and saying that we can schedule a couple of one-shots on the scheduler, and it works. And we can schedule some repeated things on the scheduler, and it works. And I'm going to do one more thing, which is schedule everything. So I'm going to reset that counter and sched add those. I'm not going to run anything. So we are going to schedule this for t plus 10, this for t plus 12. Oh, okay, and then we are going to sched add, not any of that, and counter period and until. We're going to set all of this up at the top. So 10, 12, 20, 27. After we do all the scheduling, we're going to check our counters. Then we're going to do a single run all and check our final state. Probably off by 1. Adding a scheduled event in the past is not allowed. That's because I need to put in T0 equals tau. And it all passes. So I can dump all of these on the bus on the scheduler at once. Let's mix up the order a little bit. Let's do the 27 up there, and then the 20, and back to the 12. So we can schedule things in any order, and they still come out right. So our heap is working. We're able to put things onto the heap and pop them off the front and run them around, and that's good. So how do we benchmark this? I'm going to take the built-in self-test. I'm going to start from that. I'm not interested in the onesie-twosie things, so we are going to sched init, invar, set the context up. I'm going to wipe out the first set of things. I am thinking I may want a lot more than just 2 contexts. So let's set up, say, 10 independent counter thingies that are counting at various rates. For int I equals 0, I less than nctr plus I. Let's say const int nctr equals 10. We're going to say ctx sub I dot s equals s. Get t to tau there. I'm going to add a bunch of repeaters. Sched add. Oh, all these places where I say ctx arrow s in these tests, I'm just using an external s, aren't I? Okay. CTX arrow sub I arrow S. And this is a benchmark run, not a testing run, so we're going to do that. And we're going to say sched run all. And what I need to do is limit the number of items on the schedule. But as I do the timing, I need to increase the number of loops I am running in the timing. Grumble. This doesn't fit with my benchmarking thing that I set up. See, I need to have a function I can call that runs the schedule to, well, if I run it to completion, it means I need to have sched add, which means the thing that I am timing is going to have to add things to the schedule and then run the schedule to completion repeatedly. Okay, so void bench sched if context void star CTX. What am I going to pass in for CTX on this? Probably sched. So I'm going to start out with an empty schedule and end up with an empty schedule. And this guy gets to do his own stuff with rep CTX, like that. We are going to sched add. So the benchmark is going to include adding things to the schedule initially, running them to completion for a large number of iterations, and ending up with an empty schedule. Let's build our heap somewhat bigger. Let's say we got 50 things that are going to be recycling through the heap, 50 counters recycling on the heap. And each counter is going to say CTX sub I arrow period is equal to 10 plus I. And CTX arrow, let's see, I want this to end at some point until equals, say, 10,000 divided by period. Okay. And we're going to start all of them at T0 plus 10 plus I, and we're going to repeat like that, and then we're going to do a run all. T0 equals tau, so we do that correctly. So before I actually benchmark this, let's actually verify this works. Bench sched of S. See if any of the invariants trigger off first. Constant start is not used. And that's because I stopped my build loop. Okay. So test condition failed here in sched run once. At some point during this, push to tail using tau max did not return tail. Okay, GDB. So we are in sched run 1, called from sched run all, called from bench sched at 448. So we're inside there. We'll go down. So we spent a lot of time here. So we're going to print S. S is optimized out. Okay, I've had it with the optimized out thing. Let's new makefile. Let's run the optimizer back to 0. So my tool doesn't automatically rebuild everything when I change make rules. Or when I delete everything. So I have to be a little more proactive. So now the debugger is off. We're still getting decent times. RTCNS is still taking its 18. I'm not comparing these with previous values because I don't remember what they were. No doubt I could run the recording back and see that, but I'm not too worried about it. These are still respectable times even with the optimizer shut off. So push to tail using tailmax did not return tail. We are going to go to frame 6. Oh, come on. Yeah, Emacs is sometimes a little bit flaky on which window it chooses to put something in. I really wanted to put my source over here on the right because I already had Sched up. 7. So that's where we are failing. And what I want to know is why that failed. So print S, print star S. So we have a capacity of 64, a len of 29, our bubble is 29. So we stopped the bubble at 29. Oh. When I push 1, yeah, I'm misunderstanding here. We want to run 1, and the bubble is not -1. So we're going to push the bubble to the tail. Well, the fact is that we can't just push the bubble to the tail because it's going to go to appropriate child. What we need to do is copy the tail element into the bubble and then push it down. So what we need to push down is the tail element and put it in place. So this is wrong. I was wrong about the fact that we were pushing tau max to the tail. What we're pushing there is the actual thing. So I'm going to grab the information from the last element of the tail. So int tail is equal to s arrow len -1. So special case, if tail is equal to s arrow bubble, then we're good to go. Okay, so if the bubble's at the end, all we need to do is decrease the length by 1, and we're done. Otherwise, we need to move the tail, move the data from the tail into the bubble, and decrease it by 1, and then run it around. So let's handle those two cases separately. We may unify later. S arrow len is equal to tail. So otherwise, we need to capture the data from the bubble slot. Int slot is equal to bubble. Okay. Tail is equal to slot. Then len is equal to tail. And we will then have no bubble. This is all going to get moved up into this else clause somehow. Well, the equivalent that does it correctly. So if slot is in tail. Otherwise, we need to say S arrow. We need to move it. So yeah, sorry, I didn't think through how Sched add worked. This is the problem with not working from an actual description of the algorithm. Is I thought, oh, I could just do this, and no, I can't. So push to tail. Did all of this. Let's grab at least heap and len here. I don't really need heap until here. Heap of. So what I want to do is I want to move the item out of the far tail of the heap into where the bubble is and then bubble it up. But I want to defer storing it. So heap sub tail dot. Now, things that we are writing are this is just kind of like an add. It's going to be weird. I may unify these. I don't know. At tau at is equal to at step fp is equal to fp. It's not really an add because we're not sticking it in the head. For run 1, we only accept a bubble in the head or in the tail. And actually, we only accept a bubble in the head. Bingo. The bubble is in the head. Yeah, I'm thinking that this code is so completely wrong that I'm going to remove it completely and just think about this from scratch. So if S bubble is equal to 0, then we do something and bubble. Consider the func at the tail, at the last entry, bubble from head toward tail until we find where to store that entry. There we go. More to the point, if only allow for bubble at head. Oh, bubble must be is at %d must be at head. There we go. So if we have a bubble, it's got to be at the head. Because the only other thing we could do is we've got a bubble at the head because somebody just consumed it. We've got a bubble at the tail because somebody just started inserting something in and they haven't finished inserting. So we are a valid Sched in the middle of being operated on. So our invariants work, but they're not external invariants. Hey, maybe I need external and internal invariants. Okay, and there we go. Yeah, our test conditions are going to be all over the place right now because this whole thing is just, I ripped out the guts of it. So the thing we want to grab is this. Equals. And I also want to grab this. I will remove locals that I don't need to use. Call this tail. Now, there is no single tail. It's not a FIFO. So this, in this case, the tail is the highest numbered element of the heap. When we bubble toward the tail, we may not end at tail, which is the bug that we had. I assumed we would end at the tail, foolishly. What was that? I just hit a sequence of the keys that did not work right. Heap tail.fp. So we identify the tail element, we capture its content, and now I'm going to say s arrow len equals tail. So we've now trimmed off the end. And I can say s arrow, okay? So the bubble is still at 0. Now I'm going to watch for syntax errors, unused variables, and a condition failed. So starting at bubble, which is 0, work toward the tail to find where to put AT FP. This is exactly the add function. The difference is that add, oh, it's not exactly the add function. It's the reverse of the add function. We do need to do a push to tail, but it's what the add function does when it fills in a bubble at 0. We are going to say push to tail from 0, find the location for at for this guy. And when we're done, We do that, setting the new content. This is not the thing we're going to run. This is the thing we relocated because there was a bubble in the head. So we took the guy from the tail and put it in the right place, which caused the correct children to move around so that once we're done with this, we will have a proper heap with no bubble where the head element is correct. So what I want to do also here is I want to say assert. So I'm going to say bubble equals S0 bubble. No. Let's just do this. Slot is equal to bubble. We're going to assert slot is equal to bubble. So Sched 1 push to tail. After push slot not equal to bubble. So there's slot. And now that we have done that, we do another invar check because we've changed the contents of a slot and changed the bubble, which was slot, back to 0, or back to -1. Yeah. Is that right? Bubble is at head. Grab the tail, trim the tail cell off of the list. We now have add FP and AP that we're holding. Starting at 0. Bubble is still 0. We asserted it here. We didn't do anything to change it, so it's still 0. Starting bubble, which is 0. Work toward the tail to find where to put the function. We've got at here, so that should find it. Assert slot equals bubble, just to make absolutely sure in case somebody broke push to tail. Pop the bubble and invariant. And now we have a valid thing at 0, so we can put the bubble at 0 on top of it and run it, step at run. If I were worried about this, I could capture the data before popping the bubble, but I am going to accept that we can do the step at run here to run this. So that allows us to still use step at run, which allows us a central place to check to make sure we are setting tau and all of that stuff. So here, slot undeclared. Int slot. Cap undeclared. Well, we aren't going to mess with the capacity here. Running once, we're never going to extend it, so we don't even need to worry about capacity. Okay, so now post is now failing. Huzzah. What this means is that this ran twice. So I said schedding once here at T0 plus 10. It ran it, and then it ran it again. So sched run 1. If bubble not equal to -1, so we have a bubble, we're going to move it around. What if bubble is 0 and len is 1? What does this do? Let's see what it does first, and then we'll work out how to best handle that case, because that's the case of we had exactly this case. We had one thing on the schedule, and we ran it, and the schedule should have been empty, and it didn't treat it as an empty schedule. So first off, with len less than 1, return. So we have something. We have a length which may include the bubble. We had a bubble. So tail is 0. We grabbed this data, which was not valid. So if the tail is the bubble, we're done. So if tail equals bubble, if bubble equals 0, so this says if, here, I'm just going to say if len equals 1, then we trim the bubble off the end. Okay, and we are actually done. We are not going to do a run. We're going to do a Sched invar of S, and we're going to return. And having done that, our runner thingy is running forever. Yeah. So that caused us to get into an infinite loop. So if len is equal to 1 and bubble is equal to 0, then we don't have any valid data in the heap. And we return from Sched 1, having done nothing but setting len to 0 and popping the bubble. Why am I not able to interrupt that? Need to interrupt here. So we are running forever in this location. We are at step at invar. Step at. So we're doing a invariant on step at. Really? So the step at we're looking at has an at, it has got a function pointer and an AP. And that's being called from here because we are doing a Sched invar. And Sched invar looks like this. There's S. It's got a heap capacity of 64, a lane of 16, and the bubble is at 6. So if the bubble is at 6, we must be in the middle of moving something, or we've got a bug. I'm leaning towards having an invariant for external, but indeed this is an internal invariant inside push to tail. We're doing a Sched add, we're pushing to tail. So we get into Sched add. We have a bubble. We asserted it was 0. And we're doing a push to tail. Starting from 0 with that time. So could it simply be that I forgot to set a termination point on that guy? Oh, right. I need to get to where we have a CTX. So counter is a big negative number. So maybe I didn't initialize counter, or maybe it's already wrapped around. Guess what I didn't do? I forgot to initialize counter. Okay, so now you're seeing a motivation for one of the things C++ does that C doesn't do, which is when you declare a an object, you've got a you declare an object, it initializes it. In C, if you declare an object on the stack, you get trash memory. So since I didn't initialize counter explicitly here, the counter value was trash. And the way you normally do that in C is you'll have an init function. I did not set an init function for this guy. So I am going to go do that now because that's the right thing to do, even for a test context like this. And what I'm going to initialize it to is ctx arrow counter equal to 0, period equals, and we're going to take a period and an int until pSched. So I'm going to require that data to be valid. So now we just need to be sure to call rep ctx init on each ctx we do. Counter, period, and until, and s. And I'm going to call that again each time I set counter to start. In this case, start period is 10, and until is start plus 10. So ctx1 counters at start, period is 10, until doesn't matter, and s. Actually, these don't matter because we're just doing a once on them. We don't need ctx2 until there. Counter start period is 10 until is start plus 17. Counter start period is 17, and this is at start plus, this goes to start plus 10. I think this will be more robust. That way, if I change the rep context again, it won't do weird things to me. Okay, too many functions, rep ctx init. So that's because I didn't declare it with all the parameters. So parameters are CTX period until an S. So I'm not allowing an initialization of the counter. I'm forcing that to be at 0. So this means that start plus is going to be 0. So the counter always starts at 0 when I reinitialize. That's fine. Easy way of getting back to that was to let it be a syntax error and just come back to it. Okay, done. And we're back to running again. And the only difference between our reference and our current is that we are printing out Sched post and just post and Sched bench and so on. So still working on bench Sched, which is going to be the thing that runs when I do a benchmark. Well, goodness, here's a place where I need to use the init function. So rep ctx init of ctx sub I, comma, period is 10 plus I, and until is 1, 0, 0, 0, arrow over 10 plus I, and pSched is S. Okay, so we terminate. And we are printing Sched bench, entry and exit, so this is terminating. And now I want to benchmark this call. Remember what this call does is it sets up 50, it adds 50 things to the queue and then runs them until the queue is empty, and each one of those is going to be running a bunch of times. So Sched inc repeat is going to increment counters by a lot. Now, the benchmarker is going to say how long it took for this whole thing to run, and I want to know the number of actual calls I made. So we are going to go up here and we say tau bench Sched, actually Sched inc okay, so we're going to do that. Got the bottom. We're going to go through all of these. We're going to add up all of the increments that were made, ctx sub I dot counter. So now when we do this, I can now say if printf standard error bench Sched made %LLD calls. So, and we see that it made 18324D calls because %LLUD is not a thing. Okay, so 18,000 calls to this thing, to the incrementer for this whole thing. So now we toss this into the actual benchmark. And the easy way to do that is to go grab the benchmark routine from somewhere else and see what it does. So it's going to do a RTC elapsed and print some stuff. And this is going to be bench Sched of S. And this is per call to Sched ink repeat. So the thing is that RTC elapsed starts by doing it 1,000 times, which might be a bit overkill. So let's start out by doing 10 reps instead of 1,000, because that build was taking forever. So yeah, the thing that we're benchmarking takes a very long time to run, so we need to run very few iterations of it. And this is telling me that if we have this many things on the priority queue, then it's taking 2.2 microseconds to do each one of those calls. Let's run that back. Times 0.001. And this is going to be MS because I'm going to divide this by I'd rather divide by 1,000 than multiply by 0.001. The floating point error sensitive part of me is sensitive to that. So we have 42 milliseconds per call to the big function that does all the things, which comes out to 2.3 microseconds per call. Now, I just remembered that we're currently running with the debugger on and the optimizer off. So let's grab this, and I'm going to save this for a moment. So we're going to go into GNU make file. And when we do this, I'm going to put in a little comment here that says, using -G-O0, we get this. And I'm going to raise this to 02. I'm going to leave the debugger on, but I'm going to raise this to optimizer level 2. And I need to actually do a make clean. So we compile everything and rerun it with the optimizer turned on. And now I add another comment here that says, using -G-O2. So, comparison, we see that RTCNS is still about the same. Step run gets a lot faster when we turn on the optimizer. Subs run doubles in speed. Step run doubles in speed. Step at run gets a lot faster. We still make the same number of calls, and this is twice as fast, and we're down to 1 microsecond per repeat call. So that's 1 microsecond when we have quite a lot of things in the schedule queue. So I am going to benchmark at several levels then. So we are going to make encounter a parameter that I set up here. So this is going to be int bench Sched jobs. It actually allows me to do that. That's good. I was afraid that this had to be const all the way up through. Actually, with that uninitialized, it should have had very serious problems. So what I want to do is run this benchmark for several values of these counters. How about this? I'm going to run it from one, I'm going to double it each time. So bench Sched jobs equals 1. While so up to 128 by 2s. There we go. Okay. That looks good. So what have we got here? So with just one job in the queue, we put a job in the queue, we run it. We put it back in the queue, we run it. So this is like best case. It makes 1,000 calls total. It takes 26 nanoseconds, 0.026, for a total amortized call. So if we have one job in the queue, it's nice and fast. Well, that's 26 nanoseconds. 2 jobs goes up to 44 nanoseconds per call. So not only are the number of calls going up, which is okay, we're doing more work, but the time to make each call is going up. With 4 jobs, it goes up to 82. 8 jobs, 161. So time per scheduled job is going up with the number of jobs queued. That looks like it's doubling each time. Should be order and log n. Oh boy. I think that there's a problem with my heap. Because with 128 jobs queued, my time per scheduled call should not be double of the one with 64 jobs queued. let's keep going for bigger and bigger counts. What if I allow it to go up to 20K? Could take a while to run. So 256 took 5. So when we double the number of jobs, we are more than doubling the number. Oh, this is not good. This is all. It almost means it's cheaper just to use an insertion sort rather than a heap. So there's something wrong with my heap code. Fudge. Oh, I'm running all those goddamn invariants. Ha ha! Yeah, there's something very wrong with my heap code. It's running invariants all over the place. So, Sched invar is a great function, and I like to have it, and it's great. But every time we call Sched invar, it looks over the entire content. So if we have twice as many jobs, Sched invar takes twice as long. There it is. So Sched invar is ultra slow. So what if I say pound define Sched invar of S as void S? So if I just take out all the invariant checking, here's what we get. So with 64 jobs, with the invariant checking turned off, it's taking us 21 nanoseconds per call. Yeah, okay. So I was worried about performance of this thing. Still, get up here. If we had 16K jobs, if we used schedule for everything in the system, every single signal, we saw something come in, we scheduled something going out, I don't think we'd have 16,000. And we would still be running at 50 nanoseconds per decision point. That's moving along pretty good. I would love to plot this. But first off, let's see here. I do need to have Sched invar called at some point. Well, no, because I can't call it during add. I can't call it anywhere. I literally can't call it anywhere because everything is critical path here. We get something happening, it's going to reschedule itself. Sched add is part of the inner loop. So let's start commenting this. So I'm going to make it look like the comments in, well, no, I'm not going to make it look like a comment. Here's one. So, Sched invar. Verify all invariants in Sched S. Note, this takes a long time. Do not do it in order of S arrow len. Do not call Sched invar from any code below. So I'm going to rename this to macro can be set to call invar or not. Set it to not call when outside unless debugging. So that's debug Sched invar is going to be either void s or that. Okay, so we use this macro for debugging and this macro for running. Mostly we will just be running. Live coding is still taking forever to run, isn't it? Okay. So we got all these places we could turn it on, and the assertions, many assertions are going to be debug assertions. So macro assert or not. Sometimes some things we only assert during debug. Debug assert const ... is assert const VA list. I think that's how I did it. Support.h. Hello, support.h. Yes, VA args. Okay, let's just make that expand to nothing. If the condition is something that involves something that's never used, well, we don't even want to evaluate it if we're not in debug. So what things do we not want to do unless we're debugging? Sched add, in fact, all of this stuff is critical code, so I really can't afford to test any of this. Well, extend is not critical code. Okay. So we can do the asserts down here. From here down, this is all debug code. We can change this back to Sched invar during testing. That also means that I need to scatter these calls around. We have a severe thunderstorm rolling in, so I may lose connection. Bada bing, Sched add, yada yada. Bench Sched. Bench Sched is not going to be doing invariants because it just does the benches. And this is going to say bench get jobs equals 1 while 1. So what we'll do is we'll break out of this if the total I want to break out of this when our actual test time gets long. Double TTT is equal to RTCNS. So if TTT is greater than a second break. So we will run these until a bench run took longer than a second. And we'll see how far we get with that. Okay. Cool. So we can get to 16,384 jobs before the bench run takes more than a second to run. That represents enough calls that the bench marker itself didn't make enough progress. And I've got to go back into RTC, and I'm going to set min reps to 100. So we won't do quite as many cases. So at 4096 jobs, I think 4,000 is a decent high load level for this particular scheduler. And this means that we're still doing 4 calls per microsecond. This is a big, I want to see the graph of this. I really want to see the graph of this. So let's print this in a form that I can put into CSV. So we are going to print out jobs, calls, total, put MS and AVG US are going to be the 4 fields that we print. So we've got jobs and LLD and %8.3F, %8.3F. Okay, and that didn't run because that's a syntax error. 2 commas in a row is not a good thing. And of course, the formatter likes to pull things up rather than leave them around. So we're going to do this, and that's 2 commas, and that ran. Okay, so our call time amortized for each of these services, we're calling it 5, 6, 10, 13, 16, 18, 21, 24, 27. This is doubling every time. This is going up every time constantly. That's good. I have a cat that needs to be cuddled because she's got thunder in her ears. I'll be right back. It might be appropriate for me at this time to do a push to GitHub. Git add dot git diff what all changes do we have? We have a ton of changes. I'm going to have to write a good log message for this one. But given the thunder that I'm hearing outside, I'm going to call this session. I think we have a decent schedule heap here. I think it's running well. It's tested. I like the output. I like the way that the performance cost is going up by the log of the number of entries. So git add dot, git commit. And this is add Sched. Or rather, it is debug git Sched working. Checkpoint as thunder storm rolls in. And we're going to git push GitHub. Next, you GitHub feature Sched. Boom, feature Sched. Okay, so my work is saved. Build wait loop. There we go. And the benchmark does take a bit to run because we are running until one of our test cases takes longer than a second. So it's going to take a little bit. So benchmark runs for a while. That's fine. Benchmark is supposed to run for a while. Before I merge this into trunk, I will probably plot this out and look at it and say, oh, that's good. And then I will get rid of it and I will adjust benchmark to just run. Maybe I'll run a couple of cases, like I'll run 1 and 2 to get the lower end stuff, and then maybe 50 and 100 to capture those cases, and that'll be it. Anyway, I need to shut down here for the thunderstorm. I will see you in the next one, probably tomorrow, because today's been a day. It's been almost 4 hours, and I don't want this streaming to turn into a part-time job because I'm retired. So see you later and keep your code safe.